So welcome, thank you for joining us. We are now beginning the oral presentations part of the symposium. So everyone will be coming up to present. There will be a brief, about 2-minute Q&A session at the end of each presentation. So please, we ask that you hold your questions until then. And without further ado, our first presenter is Steve.
Thank you very much for the lovely introduction, and welcome everyone. So, one big part of what we study in a field of mathematics that we like to call number theory is to solve equations. So this morning I'll be sharing with you some of the questions that I've been thinking about in my senior thesis over the past year. Imagine for a moment we're back to our high school geometry class and learning about right triangles. Recall that the side lengths of a triangle, right triangle satisfy this particular relationship, a squared plus b squared is equal to c squared. And given a triplet xyz of integers, we say it is a Pythagorean triple if it satisfies this relationship, x squared plus y squared is equal to z squared. So for example, 3, 4, 5 is such a Pythagorean triple because you see on the slides, 3 squared plus 4 squared is equal to 5 squared. So this is a question of finding integer solutions to this equation, x squared plus y squared is equal to z squared. Okay, and then we do some equation manipulation, and it turns out that this is the same thing as finding rational solutions to the equation x squared plus y squared is equal to 1. Or another way of saying this is to find rational points on the unit circle, x squared plus y squared is equal to 1. Before I tell you more about what rational points are, let's just look at some examples. For example, the Pythagorean triple 3, 4, 5 corresponds to the purple point that you can see on the slide, and the triple 5, 12, and 13 corresponds to the green point that you can see on the slide. So what is a rational point? So a rational point is a pair of points x comma y where x and y are both rational numbers. By rational number, what I mean is a fraction. So you take an integer, you divide it by another integer, that's a rational number. So 3 over 5, comma 4 over 5 is a rational point. But something like square root of 2 over 2 is not a rational point because square root of 2 is not a rational number. So we ask the question, can we find all rational points on the circle, x squared plus y squared is equal to 1? This question turns out to have a very nice answer after doing some tricks and manipulations. So the way you do this is you take any of your favorite rational number that we call t. You plug it into that equation on the slide right there, you get yourself a rational point on the circle. So everything is nice and whatnot up to this point. But the story of this field is that once you make the equation more complicated, it becomes much harder to find rational points now. So what I study is something called elliptic curve, which we'll just define as an equation of the form y squared equals to x cubed plus ax plus b, where a and b are integers, and 4a plus 27b squared is not equal to 0. So those are some pictures of elliptic curves that you can see on the slide over there. And we use the notation E bracket Q to denote the set of all rational points on an elliptic curve. The magic here is that there's actually a way for you to add points in this set. The way you do this is you fix a point O over here, and you take a point P and Q, you draw a line through P and Q, it intersects the elliptic curve at another point. And then you draw a line between O and then this point that we call P star Q, and then it intersects the elliptic curve at a third point. And that's the point that we call P plus Q. That's how you add points on elliptic curves. And it has all the properties that you'd expect. So, for example, for integers, you can just get all integers by just adding 1 to itself over and over again. For example, you can get 5 by adding 1 to itself 5 times. So in this way, we say the set of integers is generated by the number 1. Mordell proved in 1922 that the set of rational points on an elliptic curve can also be generated by a finite set of points. What that means is that in order to obtain the rational points on an elliptic curve, you can just add a finite number of points over and over to itself finitely many times, and then you can get any rational point. For example, on the elliptic curve over here, you can find all the rational points from these two simple points, minus 2, 3, and 2, 5. Then the question is, what's the least number of points we need to find all the rational points? This is a number that's known as rank, and this is a very hard question, surprisingly. to this day, we don't have a good way of finding this number rank given an arbitrary elliptic curve. So one question that we like to ask instead is, what is the rank on average, quote unquote? So let's make that more precise. For a moment, just recall how we define the average test score on the class as a question that all students ask on a semester basis. They ask their professor, what's the average score on this exam, right? So how do we calculate that number? We sum up every individual's test score in the class, and we divide it by the total number of students in the class. So we want to do something similarly to define average rank of an elliptic curve. So what you do is you associate a constant to every elliptic curve we call its faulting height. And then it turns out that the set of all elliptic curves of faulting height less than x is a finite number. So then what you do is you sum all the rank of elliptic curves of faulting height less than x, you divide it by the number of elliptic curves of faulting height less than x. And then you take the limit as x goes to infinity. So if this number exists, this is what we call the average rank. So to study what the average rank is, we need to first understand what the denominator, namely we need to know how many elliptic curves are there of faulting height less than x. Ruthie Horsch proved in her PhD thesis in 2016 that this number is, for large x, about the same thing as x to the power of 5/6. So basically what that means is the number of elliptic curves of faulting height less than x is about the same as x to the power of 5/6. In mathematics, in order to prove a large theorem, we usually need to use a lot of auxiliary results along the way in order to derive this grand theorem at the end. So what I focused on in my own senior thesis over the past semester is to improve and revise and come up with different arguments for two of the key auxiliary lemmas that Horsch used in her PhD thesis to derive this result. So I was able to find a different way that I prefer to prove something that seems very abstract at first glance. So back to where we started, is generally believed that the average rank defined this way is less than 1.5. What that means is that on average, given an elliptic curve, you only need 1 point to find all of its rational points, where it turns out that there's only a finite number of rational points on the elliptic curve. So that's all I wanted to share about my senior thesis. I want to thank my advisor, Professor David Rorlich, for suggesting this topic for my thesis. I want to thank Kilachand Honors College for providing me with this platform to share my work and my passion for mathematics with everyone. And finally, I want to thank all my friends and family for supporting me all along the way. Without you, there's no way I would have gotten here. So with that said, I'm going to take some questions right now. Yes?
So I know in math research, something we can start out not knowing exactly which theorem you're going to try to prove or try to revise, right?
Mm-hmm.
Can you talk a little more about your process of going from this very wide field of elliptic curves to this very narrow thing that you ended up working on?
Great. So that's a very good question, right? The theory of elliptic curve has a very rich history, and then there are many, many textbooks written on the subject. So there's one reference that we like to use, the yellow book that's this thick. So that's why I'm very grateful to my advisor for pointing this result out to me. So this is something that my advisor has found to be very interesting, and he always wanted to study how the proof works. So that's why he has suggested to me to look at for my senior thesis. And at first, we didn't know that there are lemmas in the proof of that theorem that we can actually try to improve. So that's something that was surprising to us along the way, and something that turned out to be very fruitful for me to work on. Yes?
Is this type of problem or this field something you want to continue to pursue in graduate school?
That's a great question as well. So I'm going to be pursuing a PhD in math after I graduate from BU, and this is a field known as arithmetic statistics. This is something very interesting, and a lot of interesting and important questions have been asked in this field. So definitely there's something I want to perhaps keep looking into in number theory going forward. Maybe one last question, a brief one, if there is any. Yes?
So I was just curious, what kind of practical applications this kind of theory is used most in for those of us who aren't mathematicians?
Yeah. So elliptic curves are used by computer scientists to develop cryptographic systems. So what that means is a way for you to securely exchange information with each other. Like, for example, how you say password or you communicate your bank password to somebody else, a third-party vendor, for instance, right? So elliptic curves are used for that. And any theoretical understanding that we can get from elliptic curves will be potentially helpful in the future for us to be able to understand those cryptographic systems better, to make them more secure, for instance. And I think that's all the time we have, and we'll resume around 10:30.